Welcome to episode 3 of this video series on variance of a random variable. In the previous videos, we looked into what is variance, why it matters, and what are different statistical moments, how they can be used to derive more information about a distribution. In this video, we look into how variance is calculated, basically the formula for variance, and how in turn it depends upon whether the data samples are coming from a population or are they coming from a sampled data set or a subset of the population. We'll also look into what are estimates and estimators, as in how estimators can be used to infer or estimate rather the true parameters of the population. So let's start with this. We have defined variance as the expected value or average of the square deviation of the samples from the mean. Now this expectation of x is nothing but the mean, so we can have this formula to be looking something like this, and we can assume that these samples are coming from, let's say, a probability distribution p of x, and if we also assume that this p of x is uniform, that means that all the samples are equally likely, and for a continuous for a discrete distribution rather, the formula would look something like this. The summation of the expectation would become into a summation, the square deviation for all the samples from the mean, and we'll divide that by the total number of samples in the population. Now, let's say for example we have these 5 numbers. The mean would be 3, and then the variance would be the sum of the deviations from this mean 3, and we'll divide it by the total number, that is 5. Now, it depends whether these numbers are actually coming from the population or are they coming from a subset of a population. Now, what do we mean by that? So let's say this we can consider it to be the whole population or the complete data set that we can have, and this would be just a small subset of the population for that we'll be using, or that we can use to uh, derive more information about the, or all the information sometimes about the population. Let's say, for example, if we want to calculate the average height of all the people in the city, we might not be able to measure the heights of all the people that are there in the city, and probably what we'll do is we'll try to just sample some people in the city, and then using these samples we'll try to calculate the height, and we'll try to estimate or guess that this is probably the average height of all the people in the city. Similarly, let's say if we have an example of calculating the average rainfall in the city, so we again might not be able to measure the rainfall in all the areas in the city, and we'll probably be sampling or measuring the rainfall in some particular areas, and then we'll take the average, and then we'll try to represent that average calculated by these samples as the average rainfall for the whole city. Now, how good is that estimate, or how good a represent it, or how good it is representing the actual parameters of the population? So let's take another example. Now, imagine that there is an alien land, and there is a scientist in this alien land. Now, a good part about this alien land is there's a big jar of cookies there, and the cookies in the jar are of varied sizes. Now, the scientist is very curious, and scientist wants to study how the cookies are, like the different sizes or different, get as much information about the cookies. Now, the scientist did a weird thing. It only picked up a couple of, or a few cookies that probably were there on the top, and it only sampled, let's say, 2 or 3 times, and it studied those cookies, the radius, the size, and different whatever the scientist wanted to calculate or measure. And then the scientist published this paper about the evidence of for the dominance of gigantic cookies in this alien land. Is it a proper thing to do? Like, the sample size, let's say, was just 5. The confidence for the whether the cookies are gigantic or not is 100%. And say they say that the cookie radius is 1.5. So let's say if it is more than 1.5, the cookies are a lot bigger than expected. So how do we define what a good estimate is? So a good estimate could, based on these examples, we can assume that a good estimate could depend upon the number of samples, or basically the size of the sample data, number of times the samples are sampled basically, and the goodness of the estimator. Now, what do we mean by that? Or let's first of all look into what do we mean by an estimate, or what do we mean by an estimator. Here, a parameter is a fixed but unknown property of the population. So, and it's actually the true value, or the truth behind this, behind the population, or like so the mean, variance, or whatever information that is there. The parameter is the fixed. It is always going to be fixed, but it is unknown because we are many a times we are not able to. Most of the times we are not able to get all the population data. So an estimator now is a statistical function or a rule that would be using the available sample data to estimate this unknown parameter. So basically, in that case, the estimate would become a guess or a measured quantity for this parameter. So an estimate, again, is estimator is a rule or a formula using this data to approximate or estimate the unknown true parameters for a population. Now there can be n number of or multiple ways to estimate the quantity or any like mean or variance or any parameter using n number of estimators. Let's say, for example, we have this jar filled with water and assume that the true temperature of this water is 98 degrees Celsius, and we want to measure the temperature of this water using a thermometer. Now, there could be n number of ways to do that. Let's say, for example, we can just simply measure the surface level temperature, or we can measure temperatures at different levels and take the average, or we can stir the water and then measure the temperature again at the surface level or at different levels. So now we see that there are different ways of estimating the true temperature of this of the water in the jar. And let's say, for example, if we use a different thermometer, then that probably might give a different reading based on the accuracy or the material of the thermometer. So again, two different thermometers might also be considered as two different estimators to measure the true value for true temperature of this water. Similarly, let's say in machine learning as well, we have known that we are having some maximum likelihood estimators to find the parameters of a neural network. Similarly, we have MAP, that is maximum a posteriori estimator. For example, if we are and there could be different ways of estimating the parameter theta for a neural network in machine learning as well. Let's say, for example, for an image classification task, if we even change a set of hyperparameters, it could be regarded as it could give us a different set of parameters, and it depends upon based on the estimators that we are using, what we actually want to achieve. Do we want to reduce the bias? Do we want to reduce the variance? Do we want to have more robustness, accuracy? And we can have varied set of metrics that we want to achieve using different set of estimators. So on a high level, estimators are just rule or statistical functions that we can have to process the sample data to actually find or approximate the true unknown parameters. Now, these estimators or estimates can be biased or unbiased. Now, what do we mean by that? So let's say, for example, we are again back to calculating the height of all the people in the city. And let's say for some reason, we only sampled people that are in this region. And this region is supposed to be people with offices. So it's mostly adult population here. And in the left-hand side, it's mostly residential. And we can assume that because it's residential, we can assume that there could be kids as well in this region. So now, because we just sample people from this half of the region, the average height for the people might be more than the average height of the people here. So it's already a biased estimate for the true average height of the people in the city. Now, we get an idea what do we mean by some notion of bias in the estimator. Similarly, if we let's assume that we have this distribution where we have, let's say we represent the height of the people as this distribution. Now in this distribution, if we sample just from this region, we can see that if the population mean was somewhere here, we are having the mean of the samples somewhere here. Again, let's say if we sample somewhere in this region, we would have the mean to be somewhere here as x4, and we can do that n number of times. We can do that multiple number of times, and we'll always be getting means at different locations, and that might not be equal to the population mean. Let's say, for example, if we just simply sample somewhere here, we might be able to get that, but it might not always be the case. So here also we can see that there is some offset or some difference in the sampled mean and the population mean that was there. But what we can also do is, let's say we just keep on sampling more and more data every time, and we can see that now if we try to take the average of all these sampled means, we can see that it might be the case that they will be somewhere here. So what do we mean by that is, so let's say if we calculate the average of all the sampled means, and we let's say do it, let's say for n times, how we can represent that as an expectation is, this is the expectation of the sample mean. We can have it to be, and this sample mean is nothing but the summation of all the samples divided by the total number of samples. And we can move the expectation inside and summation outside. Expectation of just a sample is nothing but mu. And we can see that expectation of the sampled mean is nothing but the equal to the population mean. what information are we getting from this? So we are seeing that if we keep on increasing n, if we keep on sampling more and more data, and we are calculating mean for each of the sample sets, all the sample means that we are getting in expectation would be equal to the population mean. So whenever we have such a scenario where the expectation of the sampled parameter is equal to the population parameter, then we can say that it is an unbiased estimate or unbiased. So this formula or this estimator is an unbiased estimator. So we can see that the expectation of x bar, that is the sample mu. Okay, so we missed this part. So what we have some notations here. So for population, the mean can be denoted as mu and the variance can be denoted as sigma square. Similarly, for sample, the mean can be denoted by x bar and the variance can be denoted as s square, where s is the sample standard deviation. So in this case, for unbiased, expectation of the sampled parameter would be equal to the population parameter. If that is the case, then we'll consider it to be unbiased. But if that is not the case, then we can say that it is a biased estimator. What we mean by that is expectation of the sample parameter would be equal to the population parameter, plus there could be some bias because it's not equal to that. And we'll find, and that probably we'll discuss in the next video, that if the variance is given by this formula, as in we are calculating the variance by taking deviations from the sampled mean. If you notice that this is the sampled mean, if you're taking deviations from the sampled mean, and if we are dividing it by n, this is the size of the sample data, so that's why there is an n here. If that is the case, then in expectation, this sampled variance would not be equal to the population variance. And that is why this estimator, if we calculate the variance using this particular formula, as in taking the deviations from the sampled mean, dividing it by n, in that case, it is not an unbiased estimator, rather it is a biased estimator. And we'll look into why is this the case and what we can do that to make this unbiased in the next video. Till then, happy learning. Thank you.